welcome everyone. We just heard an excellent ITC colloquium by Christoph Pfrommer, sitting over there, who spent some time apparently at the ITC corridor a long time ago. And we are very glad to have him back. We'll start today's luncheon with Pepi Fabbiano, our own from the CFA, and she will talk about imaging the hard continuum or the emission of AGN with Chandra ISO 428G014. And if you don't recognize, that's okay, she will explain. Then we'll hear from Norm Murray, who gave earlier this week a colloquium at the Black Hole Initiative that we all enjoyed, and he will talk about his lunch on fire simulations, producing carbon monoxide, which is a dangerous molecule. And then we'll hear from Christoph, who will tell us about the physics of propagating PV gamma rays, ruling out a strong intergalactic magnetic field or evidence for new physics. And finally, we'll hear from the CFA postdoc Sandro Tacchella, who is sitting over there, and he will tell us about an empirical model for galaxy evolution at redshifts bigger than 4. Pepi.
Thank you, Ali, for inviting me to present some of my science work. This is not something I'm going to talk about this afternoon. It's a program of imaging the emission of AGN with Chandra that we, at sub-arc second resolution, that we've been pursuing for a few years. So far, we've done a few galaxies, and there is a list of names, and also here is a kind of a sample of the images that we've been getting. The purpose of this work is to study the X-ray emission of the ionization cone and of the obscuring torus in Seyfert's. And some of the questions that we have been addressing is this emission due to photoionization or shocks, and which of them and how much one or the other? How obscuring is the obscuring torus? And what is the emission of the highly obscured regions, which we can probe in high energy with Chandra and the iron lines at 6.4 keV? And at the end, what we would like to do is to put some observational constraints on the mass and momentum transfer feedback from the nucleus. And here is a list of my collaborators, most of them CFA people or former CFA people. So what I'm going to talk about today is the latest of this gallery of galaxies. It's a southern barred galaxy, early type galaxy, at a distance of about 23 megaparsecs, and that means that the scale is over there is 112 parsecs per arc second, which also means that with Chandra we can probably resolve around 40 parsecs. It has a highly obscured Seyfert-2 nucleus, Compton thick, with NH greater than 10 to the 25th atoms per square centimeter. And it also is associated with a 6 centimeter radio jet, and which goes along to H alpha and oxygen 3 optical line emission. It was observed with Chandra some time ago with a shorter exposure of 30 kiloseconds, and there are two papers based on this data that they both report the presence of the extended soft X-ray emission, but they get to different conclusions. Larry David and collaborators here suggest that we're dealing with thermal emission from a hot interstellar medium interacting perhaps with the AGN or supernovae, while Levenson et al. Say that based on their spectral analysis, what we're looking at is photoionized emission from the ionization cone. Now we have a cumulative exposure of 150 kiloseconds, which is 5 times deeper, and this is what I'm going to show you. Before I go on, I want to remind you that with Chandra, we detect individually each photons, and each photon is tagged with position, energy, and time of arrival. So we have this data cube that we can slice in energy, we can slice in imaging, and in time. Here is the X-ray spectrum from 0.5 to about 8 keV. of this galaxy AGN, as seen by Chandra, and is typical of this type of galaxy, Compton-thick AGNs. What you see is a soft emission region between, say, below 3 keV, which is light-dominated in the X-rays. And this is what people think is associated with the ionization cone. Then there is a flat, featureless hard continuum that keeps going, at least in the Chandra range, and a very high equivalent with 6.4 keV line, and sometimes we see also some iron 25. Now, the soft emission below 3 keV is what traditionally people have associated with ionization cone, and that's what we also see in our studies. If we do a spectral analysis of this data, the analysis favors a mixed spectrum with largely photoionized, but with also some thermal component. The image of this part of the spectral data cube, it's here. And as you can see, is very extended at low surface brightness. In fact, extends about 5 kiloparsecs across. So this could be the ionization cone. However, it doesn't really look conical. I'm going to come back to this later. We also imaged the hard continuum and the iron line, which traditionally are associated in this type of AGNs, to the circumnuclear regions, really the cocoon of obscuring clouds surrounding the nucleus and scattering the nuclear radiation. But what we see with Chandra is that this is not true in this case, not totally. In fact, there are very extended features, both in the hard continuum over there, 3 to 6 keV, and in the iron line over here. And the extent is about 2 kiloparsecs elongated. We have to put numbers on this extent. We can just look at images. So what we've done is some kind of analysis by trying to find the optimal cone angle to distinguish between the most extended and the least extended regions. In this case, the angles are shown here. And then we do radial profiles in these azimuthal angles. And here I'm showing the example of the soft emission, where you see that in both cases, this is in log scale, surface brightness. The emission is way much more extended than the Chandra PSF in red. We just, to measure this extent, kind of arbitrarily, we decided to measure this, what we call foot width half maximum in this log plot, which means basically the place where the surface brightness is 100 times less than the peak surface brightness. And the statistics are pretty good at this point still, so I don't think we're dealing with that kind of biases. Now, here we plot the extent measured that way versus energy, and in different energy bins. So what you see here, that there is a significant extended emission, both in the cone direction, but also in the perpendicular cross-cone direction, about up to 6 keV, not in the iron line at that point. So the conclusion here is that the torus, which if you remember the standard model of AGN, the idea is that you have the nucleus, then there is this torus of absorbing material around the nucleus, and radiation escapes along the axis of this torus. While there should be no radiation escaping in the cross-cone direction, we see some. So the torus, I'd say, is porous, and so this is maybe the analogy you want to think about. This is kind of a lampshade we have in our kitchen with holes that let the radiation escape. That's one thing. Another thing you can get from this plot is something about the cross-cone transmission that can be measured. Now, for the time being, ignore the data below 1.5 keV, which is the grayed area here. Let's just look at the higher energy. from 1.5 keV above, the cone counts are 50% of the counts that we detect in the cone sectors at all energies. And since we know the volumes, and when the cross-cone volumes is 5 times larger than the cone, we can calculate that the transmission in the cross-cone direction has to be 10% of that in the cone direction. Another thing we can derive from this plot is that the extent, so the full width half maximum, gets smaller at high increasing energy. And this is nothing to do with statistics. The results are pretty solid. Just it gets smaller. Since what we see, this extent really is an image of the scattering clouds. The clouds that scatter the hard photons and the iron line at 6.4 keV. So this means that the optically thicker clouds, those that are able to scatter the higher energy photons, so we assume an NH of about 10 to 24 atoms per square centimeter, should be nearer to the galactic center of this galaxy because the extent is smaller. And in fact, in the Milky Way, there have been reports of higher, bigger, thicker molecular clouds nearer a smaller galactic centric radii. Finally, we can also look at the soft energies below 1.5 keV. And here you can see that the image becomes rounder than higher energies. So the food with cross-cone is larger, and the ratio of the cross-cone to cone counts increases to 84%. So this suggests that there is a different components here, which may be the hot interstellar medium of the galaxy that Larry David had hypothesized. And the luminosity we get from this component would be 510 to the 38 ergs per second, so it's a pretty small component. But it's interesting that this luminosity is more or less what we get also from our spectral analysis of the data in spectral space. The cooling time would be pretty large, and so it could well be energized by supernovae over the life of the galaxy. So that's my summary. I hope I demonstrated that deep high-resolution spatial imaging with Chandra can show complex extended emission features in AGNs. We've seen that in many cases. If anyone is interested, please come and talk to me later. If we look at this obscured Compton-thick AGN, we can map the absorbing and scattering clouds in X-rays. And this type of data gives us evidence for understanding both the AGN model and also the AGN galaxy interaction. In particular, in this galaxy, the torus is porous, and the cold, dense ISM scatters the hard continuum. And there is more to come because we're still working on this data. And I want to just remark here that since we're, for the next decadal survey, we're trying to push a mission to succeed Chandra, which we call links. This type of data, I think, makes the case while we need to keep the high resolution going in X-rays, while we need to also to collect bond photons. Okay, thank you. Yeah.
The thickness of this configuration may be natural if we have clouds simply moving around, and the clouds are cold, but it's the dynamics of the clouds that keeps it
together.
Yeah, and we also know of clouds in the broad line region, so it's sort of the density of clouds is bigger in some equatorial plane and smaller above the plane.
Yeah. No, I think it's totally right. For example, NGC 1365, the NH has been varying a lot. This is work by Guido Risaliti, because one of these clouds come on the line of sight. So, I mean, there is lots of this going on, clearly.
Charles, and then you.
So
Yeah.
Is there any evidence for the torus being there at all? Or is the torus a belief system based on unified media?
Well, it's a bit of a belief system, but it is true that you don't see a spherical ball of X-rays, right? So there is an elongation. And the spectrum...
But there's no waste, you know, which I think is...
No, there is no waste. That's the point. There is no waste. So that's why whatever it is, you call it torus or you... I mean, it's something that lets more radiation escape in one direction, but the other direction there are some holes. And in this case, if you go in the soft, very soft band, there's probably an extra component, which is just the hot interstellar medium of the galaxy that sits there at lower energy. So it's even rounder, but yeah.
You show that there is radio and optical emission line data on the same source. If you actually combine the X-rays, the information that you're inferring from the X-rays with this additional multi-wavelength information, do you learn something more?
Oh yes, this is paper 3 that we're working on. But I was talking with Heino. He took that data some time ago, last week. And we do see an enhancement of the X-ray emission along the radio jet. Probably not surprising. We see some regions where there is some kind of abrupt change of surface brightness that may be signifying shocks. But that's all stuff we're working on. So next talk.
There's a question over there.
I was just going to comment to Charles on the question. If you look in the optical or UV, there's much clearer evidence for waste in a lot of the type 2.
Oh yeah, that's true.
So,
in other objects, yes. Yeah.
well, the point I was trying to make though is that if you look in the optical or UV, the opacity is a lot higher per gram. And the X-rays, of course, it's much lower. You're gonna see more. Like if I go to the doctor's office, the doctor thinks I'm opaque until he puts me under
For the X-rays.
and then I'm not opaque.
Well, let's thank Pepi for
That's the thing.
Yeah, but I need the microphone.
Do you need the microphone?
All right, get started. So this isn't going to be quite as organized as Pepi's presentation. This is more just showing a bunch of results. I figured I did want to point out down here that this is mostly results taken from the FIRE collaboration. And it occurred to me that, okay, so the 4 principals are Hopkins, Faucher-Giguère, Keras, and Quater. They're all either graduate students or postdocs from Harvard. Keras is the postdoc, or was the postdoc. So I do want to highlight that this is, some of the work I'm presenting here was, a lot of it was carried out by Laura Keating, who's a postdoc at CITA, and Alex Richings, who's actually Claude Andre's postdoc at Northwestern at the moment. And then my graduate student, Gunjan Laklani, and 2 postdocs at CITA, Tove Ostol and Mubni Rahman. Okay, so these are just to show you what I'm going to tell you about. I mentioned the CO intensity mapper. We're involved in that at CITA. And one of the things that you want to know is you want to be able to predict what the power spectrum is going to look like. Because you're doing intensity mapping, you're going to mostly measure power spectra. There are predictions for how much CO there's going to be in a given galaxy or in a given halo. And we're trying to see, using a cosmological hydro simulations, with a little more detail, what you'll actually see. So that's what's shown on the right side here. On the left side is I'm showing you some chemistry calculations that using Alex Richings' code that allows us to take the simulation, which tells you the density of the gas and the temperature in the disk primarily, and predict from that, along with the metallicity, I should say, the the CO luminosity that you get out. You do some chemistry, then when you've got the chemistry settled, you do radiative transfer using Monte Carlo radiative transfer. So that's the techniques. Or maybe it's not close enough to my... Maybe it's muted.
No.
Try to turn it, yeah. Maybe a little closer, yeah. It's going to be hard. Is that a little better? Not much. I'll try to talk louder, sorry. If I just yell, then you don't need the microphone, yeah. So, as I said, I'm not going to really explain. I presume the fire collaboration has a pretty good propaganda operation. And so I'll assume that you know something about it. I just want to highlight a bunch of results that we're seeing because fire collaboration hasn't analyzed their data this way. I mean, the point of a simulation is to try to eventually make predictions. I have to say the galaxy simulation community, in my view, has a rather checkered history that way. And the fire simulation, people could accuse it of, tuning parameters. I don't think that's actually a correct accusation. But the things that people try to normally predict from these simulations are, for example, the stellar mass-halo mass relation, the star formation history of the universe. Nobody, as far as I know, paid any attention to what was going on in the ISM in a cosmological simulation, right? So I just wanted to look at the simulations and see, if you looked at them the way observers look at them, what would you see? So the first plot I show here is the upper. Again, this is a very Harvard-centric presentation, I'm afraid. This is the DAME survey. Tom maybe is around somewhere. That's the CO emission from the Milky Way galaxy. And the plot showing along the x-axis the longitude. And then the vertical axis is the velocity along the line of sight. Okay? So this is the sort of data that you get from a CO survey. The intensity, you can see there, is in these wonderful units of Kelvin per arc degree or something like that. And we analyze the data in the fire simulations the same way. You see the same sorts of behavior. It's not exactly identical. The galaxy that I'm showing you has a bit more gas in it by a factor of about 3 than the Milky Way. It's a probably slightly larger halo, although we don't actually know the halo mass of the Milky Way that well. So the first thing to say here is that it's similar. It's not exactly like the Milky Way, but it's fairly similar. You can see we're trying to highlight with this dashed line there. It's what's called the depending on who you talk to, the 3 or 5 kiloparsec ring, the CO emitting ring. We see a similar thing in the simulation of the galaxy. But I'm going to show you a lot of plots with a lot more detailed information on them. And I'm going to be comparing them to a CO catalog that Marc-Antoine Mavel-Deschênes made with Yves Lee using the DAME survey. Okay? So first of all, the point I made earlier, the upper left there is the rotation curve of this simulated galaxy. And then on there, the data points are from the Milky Way. This galaxy's got somewhat higher circular velocity than the Milky Way, so it's a little bigger. And it's a little more gas-rich. So the first thing on the top right there is the number of clouds as a function of their mass, a histogram. And the green and blue curve are from the Milky Way. That orange curve there is from the simulation. And you see it cuts off at a few by 10 to the 5 solar masses. That's just because we want to have more than, say, 16 particles in something that you call a cloud. That's a sort of not a very strong, it should be a much better result, but that's what we've got. It's also got more gas in it. You can see the histogram extends to higher mass molecular clouds. And the bottom plot shows the same thing in a cumulative graph. Okay, you can see that, again, there's more high mass clouds, but in the region where the clouds are reasonably well resolved, it does track the Milky Way pretty well. Another pair of things that observers typically show in a plot is the number of clouds as a function of their radius, the histogram. The total Milky Way is the blue curve. The green is Milky Way high mass clouds because, of course, in the comparison to the simulation, we only see high mass clouds. We can only resolve them. So you should be comparing the green and the orange curves. So there's the radius of these typical clouds. You can see it's tens of parsecs for 10 to the 6 solar mass clouds. And on the right is the velocity dispersion in the clouds. And again, the orange and the green curves are fairly similar. The blue curves have more low mass clouds. You see smaller velocities. Okay. Did I have this in the right place? Huh. I seem to be missing a slide, but that's okay. The talk will just be shorter. So I had a plot, I thought of the size line with relation, but it doesn't seem to be showing up. It's similar to that of the Milky Way as well. Okay. So I want to go on to sort of the main part of the talk, which is to measure the, so the first part there was just all at redshift 0, right? That's one place where you could actually check the predictions of the simulations. Now we're going to go extend it to very high redshift, in this case between 3.25 to 1.75, where there aren't that many, well, there are no resolved observations of CO emission. I shouldn't say none, but essentially none. And this is now plotting the CO luminosity as a function of redshift. Okay? And what you see here is, in the lower plot, as I said, the redshift along the x-axis, the CO luminosity in solar luminosities, and the red points are taken from the simulations. In this case, this is just a temperature cut, but we've redone it, and I'll show you in a second using the full chemistry calculation. It looks identical. And the CO luminosity, the black line, is a prediction for a halo of a given mass at a given redshift by Lee et al. At Stanford. And the red points are from the simulation. You can see that's a logarithmic plot over there. The amount of CO gas in the halo varies by a factor of 100 or more as a function of redshift. Okay? So if you just know the halo mass of your galaxy, it does not tell you within a factor of 100 what the CO luminosity is going to be. All right? And the top plot is supposed to show you why that's happening. Okay, so number one there is a redshift here at 2 point, whatever it is. Well, those two don't agree. Oh, no, that's time. 2.7 on the top, going down to 2.3 at the point labeled 3 there. So what's happening in this galaxy is it's forming stars at a very rapid rate, right in this region here. It's accumulating gas. And then the whole interstellar medium of the galaxy gets blown out. The galaxy essentially explodes. Okay? And that removes, 99% of the gas. That's this point 2 there. So you see in the middle plot, you don't see much CO emission. And it's not concentrated in the center where the actual galaxy is. And then it builds back up again. And at redshift 3, redshift label 3 there, it's redshift 2.25 or something. Again, it's starting to, on the next cycle, this up and down cycle. All right? So as I said, that one just showed a cut in the gas based on temperature to get the CO luminosity out. Laura has done a bunch of calculations to calculate the actual CO emission in the gas at under different conditions, trying to fit essentially the XCO factor, the conversion from the CO luminosity to the gas mass. And this is similar to the previous plot now, showing on the left there the XCO factor as a function of redshift, and then the color gives you the star formation rate. And on the right, it's the CO luminosity, which is the product of that CO factor times the gas mass. And again, you see this large, basically factor of 100 variation in the CO luminosity. You can also see from the colors, maybe not from the back, at the peaks, the star formation rate, which is on the right in the color bar here, peaks when there's a lot of gas. And then when that happens, you blow the gas out and you start this oscillatory cycle. Okay. So here's the actual mass in CO versus redshift. Okay, so the buzzer's gone off, and that's the end of the talk. Yes. So these chemical simulations are that guidance. And the first thing I'd want to do is calibrate them against observations to make sure that they're just as a sanity check. They do seem to be giving you the right sorts of values roughly. It obviously varies throughout the galaxy, as a function of galactocentric radius. It also varies with redshift, okay? And we haven't yet explored well enough how strongly it depends on the local radiation field, okay? So what we've done so far is put in a prescribed radiation field, scaled to the number of stars, or young stars in the simulation. We can actually do the actual calculation where we keep track of all the young stars that produce Lyman-Werner or CO dissociating photons. in a snapshot and just calculate directly from that the XCO factor. So we'll be doing that. That will be one of the things that will come out of this.
It would be useful if you connected to another observable or a set of observables that can help people calibrate.
So for example, one of them will be the star formation rate, right? That's already showing you this here. Yeah, you'll be able to do it by halo mass, by, well, that's not an observable most of the time. You can do by, dust emission, far infrared, which is a tracer of the star formation, but also the dust gas mass. You can do it by, you can calibrate against a bunch of other observables. So yeah, this is all certainly now doable because the machinery is all in place to do these calculations.
As long as you trust the theory.
No, you don't trust the theory. That's right. You should never trust the theory. You go to look at observations, and if it matches a lot of different things that you didn't put in by hand, then you begin to believe the theory, but you never trust it. You should know that, Abby. You're a theorist. That's right. There's too many. You know about all the skeletons in your own closet. Yeah, that's right.
So you described that you have a better method of calculating XCO. Does that actually
Better than our previous method.
better than, okay, but does it actually include the optical depth effects? I mean,
Yes, yes, it does. It does include the shielding, self-shielding and shielding from dust, yeah. So you have to close the loop. You have chemistry where you give it a specified field, then you do the radiative transfer, but then you got to go back and say, okay, the local field now is this, so you have to redo the chemistry calculation. So that's what I'm saying. If you want to do it for including all the radiation from all the stars in the simulation, that's a more involved calculation, which we have started to do now. And it's time-consuming, but it's not prohibitive. So we will have a self-consistent chemical photo, whatever you want to call it. It's not photoionization, dissociation model. But it does already include the shielding and the dissociation effects.
I wasn't asking about shielding, I was asking about optical depth in the CO line itself. Right? The CO line is...
Yes, it's optically thick. Yeah.
Optically thick most of the time.
Yes, so this is a Monte Carlo calculation. So we should be getting that effect correctly in the lines. I say should. In principle, we'll get it.
Depends on resolution.
It depends on how many photons you use, yeah. So it's just a question of computing time, right? Yeah.
And spatial resolution.
Yes, and yes. So I should, again, I assume that the fire propaganda machine has been here. The resolution in these things is, in the disk, which is where most of the CO is. It's actually pretty good. It's, tens of parsecs, 10 parsecs. I mean, the advertisement says 5, but, that's a little bit optimistic.
But you can't resolve molecular clouds.
Oh, no, well, with 5 parsec resolution you can, right? These clouds are 30, 40, 50 parsecs. Now, we're not resolving them very well. The highest resolution ones we've actually done this for are 7,000 solar mass particles, and a GMC is 10 to the 6, so it's 1,000 particles in a GMC of that size. So that's 100 particles. We do have a simulation that's mostly run with 700 solar mass particles, so then you will have 1,000 particles in a 10 to the 6 solar mass cloud. That's reasonable resolution, right? Yeah. There was another question? Oh, yeah.
So what fraction of time would that such a galaxy that is observable by Alpha or something? I'm just getting it
What fraction of the time would you be able to detect it?
Yeah.
Near those peaks. So in redshift, it's a reasonably small fraction, actually. Yeah.
So you actually can make a prediction for almost certain.
No, well, definitely. Well, so we were trying to do it for CO intensity mapping. You'll see it'll affect the power spectrum. But yeah, we could do it for ALMA as well. Yeah. You'll see fewer galaxies than there are halos of a given mass by a factor of several. So that's a pessimistic sort of prediction. Yeah.
Let's thank Norman again.
Came off. Just put it on. All right.
Thanks again. So I put up a slightly controversial topic today. I would love to hear some criticism. And so we would like to understand the physics of the propagating TV gamma rays. And this work was done in collaboration with Avery Broderick and Phil Cheng. In fact, this was started while being a postdoc at CITA, doing these astrophysics lessons. And anyway, over the last decade, we've entered astrophysics of TeV gamma rays. And thanks to these three collaborations, MAGIC, Veritas, and HESS. Now, they gave us the TeV gamma ray sky that you can see here. You can clearly see all the galactic objects. And in my colloquium, I talked about supernova remnants and starburst galaxies. I'm not going to cover about this. I'm talking about the by far dominating extragalactic component, blazars. A blazar is a jet that is pointed at us and can emit TeV photons. A TeV photon propagates through the universe, and if it collides with a photon of the extragalactic background light, it can pair produce, provided the center of mass energy exceeds twice the electron's rest mass. Now, the mean free path for this to happen is of order a few hundred megaparsecs, depending on redshift, of course. What happens next? You have now TeV pairs that move through the universe, and they will encounter the cosmic microwave background photons at a milli-electron volt. And that means you expect Compton upscattering into the GeV regime, happening on length scales that are 1,000 times smaller, so a few hundred megaparsecs. All right, so the expectation is that every TeV point source is a GeV point source. This was realized, and people, in fact, Neronov involved, looked for this. That's the intrinsic spectrum in green. The observed spectrum is attenuated due to the effect I just described, and blue is the expected cascade emission that is not seen. These are Fermi exclusion limits in 3 blazars. What's wrong? Pair production, inverse Compton emission, the same Feynman diagram, QED, we believe this is true. Well, as always in astrophysics, magnetic fields could be the reason. If there's an intergalactic magnetic field, it will deflect the pairs out of your line of sight, and therefore dilutes the GeV signal. So you expect a weak pair halo at GeV energy surrounding the intrinsic TeV point source. The stronger the magnetic field, the more there's deflection and dilution. A non-detection implies a lower limit of the magnetic field of order 10 to the minus 16 Gauss. And that excited a lot of papers that talked about primordial field, because you need to have a pervasive field through the entire universe to make this, because any given random line of sight is dominated by voids, and it's hard to make magnetic fields in these voids. However, there's a problem. In order not to overproduce the extragalactic GeV background, you need to have a co-moving Blazar density that decreases with redshift, unlike any other object or source class we know. Quasars, radio galaxies increase with redshift back to redshift 2 and then decrease furthermore. Going back to the drawing board, what could happen to a TeV pair that flies through the universe? Well, we have to realize the universe is not empty. It's filled with the intergalactic medium. So you have now the situation that there is a pair plasma interpenetrating an electron-proton plasma, giving rise to plasma instabilities. And if you work out the growth rate for this as a function of energy, it is shown here. It scales with the background plasma frequency times the coupling factor, so the beam density to the background density, times the Lorentz factor, coming from the time dilation effect. So that means the oblique, which is the dominant instability, grows with energy and exceeds the inverse Compton cooling rate by a factor of 10 to 100. If true, and that depends on where does the instability saturate, which is not known at this point, this means that the story I gave to you was wrong. Let's recap. We started with a TeV photon that pair produced of the background light, and the standard picture was that the inverse Compton cascades reprocess this emission to GeV photons. And the other mechanism I just described to you would be plasma instabilities that take the kinetic energy, put it in the collective motions of the waves in the background, and it's gone from the cascade. So the absence of GeV gamma rays have significant implications for intergalactic magnetic field estimates, which are simply absent. If you get rid of the energy, you can't constrain the magnetic field anymore. And allows, again, for a unified picture of TV blazars and quasars. It explains the Fermi gamma ray background and the Blazar number counts. So that would be a full colloquium, so I'm skipping these plots. However, the energy does not go, basically, it has to be put somewhere, and that is put into heat of the intergalactic medium. Accounting for this heating makes the universe 10 to 20 times hotter than we believe it is at mean density, which is important for the thermal history of the intergalactic medium, the Lyman alpha forest, which is a cosmic thermometer, and the late-time formation of dwarf galaxies. So that's where we were a year ago, and there was a heated discussion between these two camps. How can we decide which answer is right? Well, we have to look into the pair halo. How does a pair halo look like? So you start now with a blazar that is pointed at us. It emits these pairs that are propagating through the universe. And if there is a homogeneous magnetic field, it deflects these pairs. Now, electrons are deflected according to this green line and positrons to the right line. So a pair halo is not isotropic, but in fact a jet, where one part of the jet reflects the electron and the other one the positron emission. Now, that's easy. You stack these blazars, but wait a second. We don't know the orientation of the magnetic field, so you can't stack images. However, you can stack power spectra, because clearly such a signal has a dominant quadrupolar component, and all the even multipolar components are dominant, basically. So we stacked angular power spectra of GeV gamma ray maps of TV blazars and found no signal. That allowed us to rule out large-scale intergalactic magnetic fields between 3 times 10 to the minus 18 and 10 to the minus 14 Gauss. That's where we were last year. And then Avery had a great idea. What about the other type of AGNs, radio galaxies? They have an oblique jet. Now, if they emit isotropically for a small-scale field, we also see a structured pair halo. You just need to stack more of those. But there are more radio galaxies in the universe. So we took the VLA first survey, 50,000 sources. We selected 9,000 isolated radio jets that did not have a strong gamma ray source within 2 degrees. Aligned those sources, stacked the GeV gamma ray images. And what did we find? First of all, we can align those. That's one VLA first radio jet. That's another one, and that one is a little bit strange, so we dropped that kind of object from our sample. This shows the stacked sample at radio frequencies. So we can align and stack those sources, that's fine. What did we find for the stacked GeV emission? The top left is the unrotated stacks. You don't expect to see a signal. The top right is a randomly rotated stacked sample. And because both of them are similar, there's no issue with the backgrounds that would have shown up on the top left and not in the top right, because they average out. The bottom left is the aligned stacked image, and there is no signal. And we would have expected to see this signal. That's interesting. What does it mean? Well, we can now look at the angular histogram. And the data is here, the expectation is clearly ruled out. And so is it using then the angular power spectra. And you can see that the even multipoles, 2, 4, 6, 8, etc., dominate and are clearly ruled out by the aligned stacks. These are the black data points. What does it imply? Well, in fact, this gives us an upper limit on the intergalactic magnetic field of 10 to the minus 15 Gauss, independent of correlation length. You can ask me why. And that's the money plot I want you to take away. That's the constraint in the magnetic field and coherence length plane. This one is from magnetic diffusion. You can't have magnetic field smaller than this. Zeeman splitting, Hubble horizon. These are the lower limits from the Neronov and Wolf paper explaining the absence of the GeV bumps in the Blazar spectra. And our work now is in red an upper limit of intergalactic magnetic fields. And you can see either the universe is highly fine-tuned or there's new physics needed. What do I mean by new physics? Potentially there are plasma instabilities that dissipate this energy away and they resolve this conundrum. And I'll leave it there and wait for your questions and hopefully some critical ones.
So Christoph, the signature of a good attorney is that that person can present the opposite case as well. And so I remember we used to have a postdoc in our group named Zeroni.
Oh, yes. Yes. So the issue that is still not yet settled is the issue at which level do these plasma instabilities saturate in a nonlinear regime. If they saturate too early, they're there, but they do not suck enough energy out of the cascade, energy out of this sort of moving beam, therefore the cascades survive. Now I presented to you an observational argument that tells you they're not there. So something must remove this energy from the band. Now, this may be in conflict to the simulations, I agree. We have, in fact, not we, but a grad student of Avery Broderick, Mohamed Shalabi, wrote a PIC code, and he realized a secret in the PIC community. How to put this? Basically, it's important to know what you can trust in numerical simulations and what not. And in order to do so, you need to understand what is the sort of right way to check convergence. And we found out that in order to have a converged PIC simulation, you need to actually, for these things, to do three things. You need to increase the number of cells simultaneously with the number of particles per cell, and you need to increase the box if you are trying to simulate just a narrow instability width. And that means per dimension, it's a factor of 8. That's what we found, and that's something which the PIC community hasn't realized before. So it could have been, but this needs to be checked now, that the saturation that they found was due to numerical effects that drained energy from the beam particles, because the energy non-conservation in the Tristan code is something that is under discussion at this point. Yes, absolutely. But it's a hard problem to say. I mean, plasma physics is something you can really spend your life on and still don't make a lot of progress. Absolutely, and we still don't have yet a fusion reactor here. Absolutely. But you know what? I mean, the reason why it doesn't work is because there was always another instability found. So nature finds a way to remove the anisotropic particle distributions, and that's what we rely on here. So we are, in that respect, on the safe side. Yes.
Why can't totally randomized magnetic fields erase any evidence of cascades? You were showing us ordered fields, which I think would be all the more difficult to imagine in the first place.
So that basically assumes a small-scaled disorganized field. So within this jet, you would isotropically emit this emission. That means you will also emit the emission into our line of sight. And stacking enough of those is enough that we should have seen a signal if the magnetic field was above 10 to the minus 15 Gauss. So we get therefore an upper limit on the magnetic field. And together with a lower limit from Neronov and Wolf, that basically rules out magnetic fields in most of this parameter space except for here. So by the way, that's an upper limit on the coherence scale, which is at, if you have a magnetic field that is at the quantum chromodynamic phase transition or electroweak phase transition mate, it's there. But if you allow for magnetic diffusion throughout the universe, you can basically sort of open up this little spot in parameter space, which of course would require fine-tuning, which may or may not be true. I don't like fine-tuning.
Doesn't this depend on the strength of the infrared background that we don't really know very much? Also the extension of the TeV from the Blazar, which is just surmised to continue
So yes, there are lots of uncertainties. I completely agree. But that's the least I worry about, because that has now been measured to a high precision. And so it's certainly better than a factor of 2, especially in the infrared, which is important for the TV cascades. In the optical, it's a little bit less certain, but we don't rely on this part. We rely on the infrared part. And I think the best measurements now come from the from stacking AGNs at different redshifts and looking at how their spectrum is softened with increasing redshift.
Hello. So thank you very much for giving me the opportunity to present some very kind of recent work that I've been doing in collaboration with people actually here at the CFA. So in particular, Sonak Bose, Charlie Conroy, as well as Daniel Eisenstein. So as when we look at the cosmic star formation rate density in the universe, we see at recent times this very strong decline from redshift 2 to today's epoch. And so this decline can be explained by 2 phenomena. One is that individual galaxies have lower star formation rates, which are probably caused by lower accretion rates onto the galaxies themselves. And the second part to this is also that some galaxies actually totally switch off their star formation. Now, we can also see this when we look at today's galaxy population, that there's this bimodality between color, star formation rate, and the morphology of galaxies, where the quiescent galaxies that are not forming stars anymore are usually showing early type-like morphologies. Now, really, we don't really yet know what really brings the star formation activity in galaxies to a halt. And one way to address this question, which I've conducted in the last few years, is to go to higher redshifts, in particular at the peak of cosmic star formation, redshift of 2, where we now are able, with current technology, in particular the Hubble Space Telescope, but also ground-based instruments such as the VLT, to map out the stellar mass and the star formation and distribution about the kiloparsec scale. And so from these studies, we have actually learned that in the central part of these galaxies, there are already very high central densities of the order of that are comparable to local early type galaxies. And the star formation usually is distributed more in the outskirts in a disk-like profile. And so we believe that these galaxies are switching off their star formation from the inside out. Now, what exactly forms their bulge component is not very clear yet. We put forward, based on numerical simulations with Avishai Deckel, that it could be because of gas compaction events that are triggered, for example, by mergers or even counter-rotating streams that are leading to gas inflow into the central region. Now, in order to make progress on this, would be, of course, very useful to push such resolved studies to higher redshifts. Now, currently, we are very limited, especially in the 1 micron to 6 micron regime, because of spatial resolution. And we look here, for example, this is current technology with Spitzer, showing a kind of the regime of 3 to 6 micron. This is what we see of the current sky. This is all mocked up from the illustrious simulations. With JWST, of course, this will be a very different story, and it will be really a game changer to do spatially resolved stuff. So you can see here, this is now the same kind of image, but with resolution coming from the JWST. Now, questions that we can answer with JWST will be, of course, a long list. I just show here a few of them that I'm interested in to study in the next few years. In particular, it comes to questions down like how do really first bulges and disk components form in galaxies, and also why do some galaxies switch off their star formation already at early times. Then something else what we want to do is, of course, quantify morphology at the rest frame wavelength. At the moment, we just really see the UV light of these galaxies, and so we want to really go into the optical, where most of the stars actually emit their light, to really understand their size distribution, how the sizes change as a function of time. Now, for the rest of my talk, I will be focusing actually more on kind of galaxy formation models at higher redshifts. In particular, we will learn much about number counts of high redshift galaxies. At the moment, we have detected of the order of maybe 9 candidates at redshifts of about 10. And also stellar mass estimates that are crucial, to kind of understand whether the numerical recipes that we have in simulations are really working well at these high redshifts. And so what I show you here is now an empirical model, that really, the basic idea is to link some observed galaxy property, for example, the UV luminosity, to the dark matter. Now, the idea is to have simple parameterizations that are, enable you to kind of marginalize over poorly understood physical processes. Now, I think, at least for the model I show you now, is that there are three very useful things one can do with it. The first thing is one can really start, thinking of planning future surveys. Now, of course, JWST, expecting number counts, but also missions that are maybe still, on the plate, or like probably first. Then it helps you really to interpret observations, and this includes understanding observational biases that we have in our samples. And then finally, it helps you to constrain relevant physical processes in numerical methods. So for example, such a model can give you a stellar-to-halo mass relation, which we have heard before already, can be useful to understand whether the simulations are in the ballpark where they should be. Now, this is not like a first empirical model has been developed for high redshifts. We have done some work ourselves in this previously. I think what we go beyond now is really to understand not just the UV luminosity output but also looking into stellar properties like the stellar mass themselves, and also going from simple extended projector formalism to really numerical simulations. And so the basic idea is to really have some efficiency, or model the star formation rate of a given halo at the given redshift by the efficiency times the dark matter halo accretion rate. Now, this is written in a very flexible way so that we can use all kinds of n-body simulations. I'm currently using the color n-body simulations, and has a box size of 100 parsecs, 100 megaparsecs, and a dark matter resolution of 6 × 10⁶ solar masses. Now, the efficiency, as you can see, is redshift independent, and this is a big assumption in our model. So we just assume that it depends on halo mass, and it would be nice if we are able to rule this out. And as we'll see, that this is actually at the moment with the current observations not possible. But so this efficiency is then calibrated via the UV luminosity function redshift 4. And so this really means that we are coupling the star formation history of a halo with FSPS, so for some stellar population modeling, to the UV output of these halos. And then we can calibrate this efficiency so that we match the UV luminosity function at redshift 4. Now, how do we do when we just check the UV luminosity function itself? So of course, by redshift 4, we do it by construction. And now we just run the model forward, or actually, see how it does. So redshift 6, for example, we do still very well, redshift 8 as well. And so this is really meaning that we don't change the efficiency. We just have it fixed, what we get from redshift 4. And what changes is really just the dark matter structure, kind of the accretion of dark matter as well as the number density of halos. Now at redshift 10, you see there is still a lot of uncertainty. This data point comes from the Hubble frontier field. This means that they are looking behind clusters at a rather small volume. These points here come from all the most of the HSD data has been taken in the past few years. So these are 800 square arc second imaging data from Hubble Space Telescope, detected 9 galaxies or candidates at redshift 10. And so our model is somewhere in between at the moment, but this of course is still quite uncertain, at least observationally. Now we can also look into this from a different angle, the cosmic star formation rate density. As a function of time. And so these are different data points. This is our simple model. If we would just look at the green points and, for example, take the model and just extrapolate, you would actually kind of overpredict. And some models actually really do this. So you get a quite high cosmic star formation rate density at these early times. Now, we cannot really rule out these models yet because, as I said, the uncertainties on these data points, I think, is larger than what is indicated here. But actually, when you look at different models, also what has been done has been here, like by Emission et al. 2016, models that usually take into account the halo mass function evolution, they usually are able to reproduce this rather fast turn down. And in a simple way, this can be understood by just that the halo mass function, if you look at this efficiency, the halo mass function, this the knee of it is moving into the regime where more and more halos are able to form stars efficiently. Now, we can go on and then start talking about number counts. So here I show you 2 surveys that will be conducted with JWST very early on, and I'm involved in. This is the JWST Advanced Deep Extragalactic Survey, which is really coming from a joint program of the NIRCam and NIRSpec GTO teams. And so this includes 800 hours prime and 800 hours parallel NIRCam, NIRSpec, and MIRI observations. And so there is a deep and a medium observational plan, as well as CEERS, which is an ERS program led by Steve Finkelstein. So there are, it's a smaller program, but it has similar, it's a similar layout like this. It's 35 plus 35 hours. And so when we look into the number counts, what you can expect is of the order of 1,000 redshift 8 galaxies and of the order of 100 redshift 10 galaxies within about the first year of JWST. Now, moving on, and beyond the UV luminosity function, something interesting to look at is, of course, the stellar mass functions at these redshifts. Now, as you can see, observations, even at redshift 4, have a large, discrepancy. They are not agreeing at all with each other, and this is because they drive stellar masses in different ways. There are large uncertainties coming in from, exactly what the redshifts actually are of these objects, star formation histories, metallicities, IMF, dust, and so on. Interestingly, our model at the moment, at least, seems to, really favor higher stellar masses at these redshift. But as I said, this is all preliminary, and I think what is very important is to take into account effects from metallicity and so on, which is still on our list to do. But overall, we have rather a steep bending slope that gets steeper when you go to higher and higher redshifts. So last but not least, I think something interesting to look at is the stellar to halo mass relation. And so this is really, the fraction of stellar mass to halo mass, function of halo mass. And so the gray point shows you kind of the number density, the number of objects we have in each of these bins. The blue line shows you the median of this relation. Comparing it with other empirical models, especially coming from lower redshifts, for example, the emerge model from Mostre et al., this model is much more, complicated because it really wants to explain galaxy evolution down to redshift 0, including satellites, central, star-forming, and quiescent galaxies, which we don't do in our model. And so these models seem to have a lower stellar to halo mass relation at these redshift 4. Now, an interesting constraint comes from some observational work. This is based from star formation histories from dwarf galaxies in the local universe. So they are able to, map out the star formation histories rather accurately and get stellar masses for, their past history. And, these kind of observations actually imply a much higher stellar to halo mass relation. And now, just, to the end, I show you kind of where current simulations lie. And so they lie kind of, all over the place a little bit, but it's quite interesting that there is a lot of diversity in these simulations. Okay, so my time is up, so I'll just show you some conclusions. So at the moment, the simple empirical model is able to describe the current observations. What it puts forward is really that the key driver of galaxy evolution at these early times is really, kind of linked to the dark matter buildup. And so at the moment, at least, we do not find any indication that we have to invoke a redshift-dependent efficiency in converting gas into stars. And with JWST, we can expect, at least in the first year, of the order of 1,000 redshift 8 galaxies and 100 redshift 10 galaxies. And the neat thing is, especially with the GTO team, is that we can not just get the imaging and the photometric redshifts, we can actually follow them up within a few months after with near spec, so we can get also spectra for them to make them sure that they are at these redshifts we claim. Thank you very much for your attention.
Looks like we shouldn't feel special that the Milky Way galaxy is the most efficient factory for star formation, and it's sort of natural for us to be in such a galaxy.
Yeah.
Where should be around a younger star.
That's right. That's true.
Yeah, but I said, so such a model, kind of ignores all these interesting effects, that of course, why is there this, of this efficiency? Why do we, believe that there is a turnover that can go roughly 10 to the 12 solar mass and halo mass, which maybe is linked to, some AGN feedback at high mass and more like supernova at low masses. But all these, I say, periodic processes are ignored in such a model, and I think are important to be analyzed, by further numerical simulations.
Questions for Sandro?
So you show predictions for different models, and if some of those are ruled out, can you tell us what we'll learn about the physics of galaxy formation? Or is it just this point that, this one, where the arrow is?
Yes. Something which would be interesting to understand whether really this efficiency for gas into stars will be evolving as a function of time. So in this model, we assume it's not, and this is kind of the simple numbers we get. But something we have to really explore much more is the whole business on metallicity and IMF variations. Especially when you think about metallicity, they can change the UV fluxes significantly, and therefore also give you some trends, concerning, kind of what you expect from going from a UV luminosity to a star formation rate. So all these conversions that are used at the moment, are also kind of up in the air, and I think must be analyzed again. So what I'm trying to say is that, it's hard to rule out at the moment, kind of these simple models, also because there's a lot of wiggle going from simple galaxy properties to fluxes.
And those other models that you showed, from Peter Barossi and people, what do they assume they make very different predictions to yours?
Okay, so yes, so with the Brucey model, I'm not sure yet. So they are updating their model at the moment. A lot of it has to do also, you know, that when you fit those models with an MCMC and you put in some observational constraint, that those are mainly coming from lower redshifts. And so these high redshifts are usually kind of extrapolations. And so, you know, it could be that, you know, they're weighting certain properties differently.
We will all keep our fingers crossed that JWST will fly in a year, and we'll have plenty of data to work with.
Yeah.
Let's thank all the speakers.